might come later. So, okay, so good afternoon, everyone. So today I'm very glad to have Dr. Bersano here to speak at the ENEA seminar at the University of Wisconsin-Madison. So Dr. Bersano got his master's degree from the Energy and Nuclear Engineering at Politecnico di Torino University from Italy, and also a master's degree from mechanical engineering at the University of Illinois at Chicago. And then he got his PhD in the energetics at Politecnico di Torino from Italy in 2020. And now he joined ENEA to working on the passive safety for the advanced reactor. Today he will talk about his work about the ANSYS of passive safety system for advanced nuclear plants. And let's welcome our Dr. Bersano from Europe. Thank you.
Thank you for your very kind introduction. And I will try to share my presentation. Okay, can you see it? Okay, great. So thank you very much again for the invitation. And my name is Andrea Bersano, and I'm from ENEA, as Dr. Wang just mentioned. And today I will try to present some insights about the use of passive safety system for advanced nuclear plants. And I will try to say something about how we can analyze this system, in particular from the thermal hydraulic point of view. I will use two examples to show how this analysis can be done, both considering the validation of computational tools and also the quantification of the uncertainty of the results. So as you may know, passive systems comprehend a large class of systems that are very powerful because they do not require external energy to operate, because they rely on physical principles such as, for example, gravity for the injection, natural circulation for the heat removal, boiling and condensation again for the heat removal in heat exchangers, and so on. Passive systems are not extremely new because they've always been adopted in the nuclear sector. For example, the hydraulic accumulators for the mitigation of the loss of coolant accident. But they received a very strong attention, in particular after the Fukushima Daiichi accident, because of their intrinsic safety and the possibility to increase the safety of nuclear plants. And in fact, some advanced reactors, such as, for example, the P1000 or SMR, such as the NuScale power module, largely adopt passive system to mitigate the consequences of possible accidents. So there is not a unique definition of passive system, but probably the most known one is the one given by IAEA. So a passive system is either a system which is composed entirely of passive components as structure, or a system which uses active component in a very limited way to initiate the subsequent passive operation. So this is a kind of broad definition. In fact, the IAEA classifies passive system based on different categories. In particular, there are 4 categories of passive system with a higher degree of passivity. So from the no mechanical moving part to no mechanical, no moving fluids, and so on. But this is a quite broad definition, and then each passive system may be classified based on the level of passivity, both for the operation and for the activation, because as we just said, an active initiation can be used to activate a passive system. So they have some recognized advantages and some drawbacks. Among the advantages, in general, they have a simpler design with the elimination of several or a certain amount of component that simplifies the design of the passive system. They should have, in principle, a higher reliability, and so for this reason, they are attractive for nuclear safety. As we just said, we don't have external energy sources for their operation. And we have a reduction of the operator intervention, because this system should be automatically activated. So in this case, we have a lower probability of human error related to the operation of this system. And finally, since this system should increase the safety of nuclear plant, there is also probably a perception of a higher safety level from the public, and so they should bring also a higher public acceptance of nuclear plants. However, there are also some drawbacks that should be considered. In particular, one of the main drawbacks is the fact that the driving force of the system is substantially lower compared to active systems. So if in a normal decay heat removal system, we have a pump that circulates the water, in a passive decay heat removal system, we have natural circulation, that is the driving force. And the driving force is up to 2 orders of magnitudes lower with respect to an active system. Also for this reason, and for some issues related to the analysis of passive system that we'll see afterwards, their reliability is not so easy to be determined. And the reduction of operator intervention, if from one side is an advantage because we have a lower probability of human error, on the other side makes this system quite hard to be controlled. So once the system is activated, it should operate without the intervention of the operator. And so on the other side, is not so easy to control and eventually to regulate the performance of these systems. There is the need for better manufacturing of the components, because this is related to the first point of the drawbacks, so the lower driving force. Since we have a lower driving force, we need, for example, to have a very low roughness of the piping, very low local loss coefficient in order to achieve natural circulation. So we need also some better manufacturing of the components. A more controlled installation, because it's more important to ensure, for example, a perfect verticality or horizontality of the components. And finally, since we have a lower driving force, passive systems are more prone to thermal hydraulic instabilities with respect to active ones. So in an active system where you have a pump that pushes the flow of your fluid, you can have instabilities, but in a passive system based on natural circulation, it's more likely to have these instabilities. However, in general, advantages are recognized to be higher than the drawbacks, and this is the reason why passive systems are more and more considered to be installed in nuclear power plants. In particular, deterministic safety analysis of these systems are carried out adopting thermal hydraulic codes, at least for the thermal hydraulic analysis. And these codes were developed in the past, in particular in the 70s and 80s, mainly considering the phenomenology typical of active system, because we said that passive systems were adopted in nuclear plants, but mainly for the hydraulic accumulators. So there were not other relevant passive systems in the traditional plants. And so the deterministic codes that were developed to carry out safety analysis were mainly devoted to the analysis of active systems, such as, for example, high-head safety injection system, and so on for the mitigation of LOCA. So in order to employ this system in nuclear power plants, we need to prove that our codes are able to predict the phenomena typical of this system. So we need to validate our computational tools against the available experimental data to demonstrate that these codes are able to properly simulate the behavior of passive system, and therefore to prove that these codes are able to predict the behavior of plant equipped with passive systems. And in particular, at the beginning of deterministic safety analysis, it was adopted a conservative approach to carry out this analysis, in particular due to the lack of knowledge of some physical phenomena and the lack of some experimental data, and also the low computational power that was available back in the past. However, on one side, there has been a very strong improvement of our computational capabilities, and on the other side, also the knowledge of thermal-hydraulic phenomena has been significantly improved by the several national and international activities that have been carried out with large experimental facilities to understand integral effects, and also the separate effects test facility for specific system or for specific phenomena. And therefore, now it is possible to use a more realistic approach for the simulation of this kind of system, but in general, to carry out deterministic safety analysis. And this approach is known as best estimate. However, even if we did significant improvements in our knowledge and in our simulation capabilities, we still have some lacks in physical phenomena, in closure equations, and so on. Therefore, we cannot just make a single calculation and consider its result as the real value of a parameter, such as, for example, if we make the example of loss of coolant accident, if we make a calculation and we consider the results of the peak cladding temperature as the real value that we can expect in a real transient, that's not sufficient, but we need also to quantify the uncertainty on that result. So this approach of using a best estimate code and quantify the uncertainty of the result is known as BEPU, best estimate plus uncertainty. And basically on the right-hand figure, you can see the benefit of this approach. So if on one side we have the conservative code result, we have the best estimate code result that we hope it is farther from our safety limit and the regulatory acceptance limit. And also considering the uncertainty on the best estimate calculation, we hope that the uncertainty will not cover the conservative code result. So the difference between the conservative code result and the upper bound of the uncertainty is the benefit of this approach that can be translated, for example, in power up rating and so on. But before doing the uncertainty, it's fundamental, as we said at the beginning, that we are able to prove that our tools can simulate the phenomena occurring in passive system in order to correctly predict the behavior of plant equipped with passive system. So before the uncertainty is fundamental, the validation of the code, and in particular, the evaluation of the accuracy of the code, that is basically the known error that we commit when we apply a code. So when we apply a code, we know that we are committing some error, and in particular, the accuracy is the known error that we are committing when we apply a code. And we can evaluate this error because normally the accuracy is calculated against experimental data. So we know the values, we know the experimental result, we perform a calculation, we perform a simulation, and so we are able to compare the experimental data and the calculated one, and to compare, and so to evaluate the accuracy of our calculation. And in particular, normally the accuracy is evaluated in 2 steps. So the first step is the evaluation of the qualitative code accuracy. And basically, the qualitative code accuracy evaluation is based on the evaluation of the capability of the code to predict the involved phenomena that are present, for example, in an experimental transient. After the qualitative evaluation, so if we assess that our code is able at least to predict the involved phenomena, we can pass to the quantitative evaluation, the quantitative accuracy evaluation. And so the quantitative accuracy evaluation allows us to say which is the value of the error that we are committing in the application of our code. And so for the quantitative accuracy evaluation, there are several possibilities. Today, I will show you some application in which we adopted the FFTBM, fast Fourier transfer-based method, to evaluate the quantitative accuracy of a code. But despite of the method, the takeaway message is that before doing any uncertainty quantification, and in any case in which we are validating our computational tools, we should assess which are the performance, both from a phenomenological point of view, because our code should be able to predict the phenomena that are observed in the experiments, and also from a quantitative point of view, because we also need that our code are able to predict correctly the values of the main thermal hydraulic parameter that we can expect during a transient. Then, as we said, it is possible to calculate the uncertainty of a code. And while the accuracy is, let's say, the known error, because we can compute it if we have experimental data, the uncertainty is basically the unknown error that we make when we apply a code to perform an analysis. And there are always some sources of uncertainty when we apply a code. So basically, uncertainty is something that is unavoidable. And these sources of uncertainty normally can be grouped in the uncertainty within the code itself. So basically, there are approximations in the closure model and correlation. There are some numerical approximations and so on. There are uncertainty related to the representation of our plant. So when we model our plant, we should make normally a trade-off between the complexity of our model and the time that we have, that we need to solve this model. So there are always some uncertainty due to the nodalization or the schematization of our plant. There are some uncertainty related to the scaling issue. So we said that in the accuracy evaluation, we have experimental data. So basically, all our codes are validated against scaled down facilities. And when we apply our codes to full nuclear power plants, there might be some sources of uncertainty related to the different scale between a full nuclear power plant and the experimental facility. There are some uncertainty related to the plant itself. In particular, it's very hard to know all the initial and boundary conditions that we have to impose in our simulation. And finally, there is also the user effect. So even if the codes are validated, the different user may introduce some sources of uncertainty, because each user will model a different component or a different system, probably in a slightly different way. And so also the results will be slightly different. So for this reason, in the past, several methodologies have been developed to perform uncertainty analysis and to quantify the uncertainty of the results. And in particular, they are normally divided into methods to propagate the input uncertainty. And I think it's better explained in this figure on the right-hand side. So in a normal input deck for a thermal hydraulic code, we have really a lot of parameters or a lot of values that we have to enter, and it may be in the order of 10 to the 5th. The idea of the propagation of input uncertainty is to select, let's say, the most relevant input parameters, or the input parameters that we expect that mostly affect the results, and to propagate the uncertainty of these parameters through our thermal hydraulic codes that have been previously validated. And in this way, we are able to construct the uncertainty on the results. These are the methods to propagate the input uncertainty that are then subdivided also in probabilistic and deterministic method. And in the following examples, I will show you some application of the probabilistic method to propagate input uncertainty. And the other category of uncertainty quantification method are the methods to extrapolate the output uncertainty based on experimental results. In particular, now I will use two examples to show an application of this concept of accuracy evaluation, uncertainty quantification, so on. And these examples are carried out with two quite widely known thermal hydraulic system codes, such as RELAP 5 3D and TRACE. And these codes have been coupled with uncertainty tools such as Raven and Dakota to carry out this uncertainty quantification. So the first example is the PERSEO facility. So PERSEO, that means In-Pool Energy Removal System for Emergency Operation. And is a facility that is located at SIET Laboratory in Piacenza in the north of Italy. And it is a very important experimental facility for the analysis of passive system, because it's a full-scale facility that was designed to test a new decay heat removal system. And the objective was to move the system activation valve from the high pressure primary side to the low pressure pool side. It's a very relevant facility because it has a maximum thermal power of around 20 megawatt. And so it's a very huge facility, one of the biggest test facilities for passive system. And considering the thermal hydraulic condition for its operation, it can operate at conditions typical of the primary side of a BWR or the secondary side of a PWR. So basically, this is a sketch of the PERSEO facility when it's not in operation. So in this case, it's connected to the primary side. And when the system is not active, the valve connecting the two pools is closed. And so in the pool where the emergency heat exchanger is located, there is no water. So therefore, a heat transfer from the emergency heat exchanger to the pool is negligible because there is only air. And when the system is activated by the opening of the valve between the two pools, the pool with the emergency heat exchanger is flooded, and therefore it starts the heat transfer from the heat exchanger to the pool side, and also the natural circulation both on the primary side with steam entering in the top of the heat exchanger and condensing through it and going back to the pressure vessel. And also we have natural circulation on the secondary side because the boiling in the heat exchanger pool, we have boiling in the heat exchanger pool. The steam is directed in the overall pool that is it's kind of water reservoir where it is condensed again. And so we have a second natural circulation path between the two pools. Basically, the data collected in this facility are extremely useful for the analysis of the behavior of heat sinks of passive system because they allow us to study several phenomena such as, for example, in-tube condensation in the emergency heat exchanger, nucleate boiling on the pool side, the thermal stratification that we can have in the two pools, and also due to this very specific configuration, also the dynamic of these two coupled pools. And in particular, among the available tests, two of them have been analyzed by RELAP 5 3D. And in particular, today, I will show you test 7, that is a full pressure test at around 70 bar. And in this full pressure test, basically, we have all the possible phases of the system operation. So in the initial part, we have the system activation with the filling of the heat exchanger pool, the quasi-steady state system operation with the heat exchanger that is completely submerged by water. And so we have the maximum exchanged power, and then we have the system deactivation. So this test is very interesting because it allows us to evaluate the capability of our code in the different phases of the system operation. Here is just a representation of the nodalization that was developed for ReLab 5 3D. So the nodalization is the way that we adopt to geometrically reproduce our system in such a way that the code is able to solve our model. And here you can see all the different components that composes the experimental facility that have been replicated in this nodalization. So an interesting thing that came up is that if you remember at the beginning, we said that these codes were developed in the past having in mind active systems. So having in mind the geometrical dimensions of active system, having in mind the operating condition of active system, and so on. So when we try to apply this code to this passive system, what we saw was a significant underestimation of the heat exchanger power that was nearly half of the experimental one. So just trying to reproduce the behavior of this facility, our code computed the power that was half of the experimental one. So in case we don't have experimental data, we may think that this is the real value of the power that is exchanged by our passive system, but in the reality, it was half of the real one. And after an analysis, this underestimation has been attributed to the underestimation of the condensation heat transfer coefficient within the heat exchanger tube. And this is exactly related to the different operating condition that we have between active system and passive system. So in this case, in order to reduce the frictional pressure losses, because we said that the driving force is lower in passive system, the tubes are relatively have a relatively high diameter, and therefore the steam velocity within the tube was relatively small. And for this reason, the code was not able to correctly predict the heat transfer coefficient. Therefore, different correlations have been tested to evaluate in order to try to correct the result. And it has been computed a correction factor based on the different correlation in order to allow the correct prediction of the power of the system. And in particular, in this case, 3 different condensation regimes have been considered. So for the laminar regime, the Nusselt equation has been adopted. For the laminar wavy condensation regime, the Kutateladze equation has been adopted. And for the turbulent regime, the Chen equation has been adopted. And after a calculation of a correction factor with the different sets of equations, it was finally possible to correctly predict the behavior of the system. So in particular, if you compare the original simulation result was the solid blue line, and the corrected simulation result is the orange dashed line. That is, it's very close to the experimental results. So in this case, it was able, with the correction factor, we were able to correctly predict the experimental data. And this is very important because if you want to analyze the passive system behavior and to carry out deterministic safety analysis, it's fundamental that we are able to predict not only the phenomena, because the condensation was predicted also in the original simulation, but also the quantitative value, for example, in this case, of the experimental power. So here you can see that after the application of this correction factor, we are able to predict the behavior of the main thermohydraulic parameter. So the increasing water level in the heat exchanger pool at the system activation with the consequent increment of the heat exchanger power, the quasi-steady state system operation with a nearly constant water level and heat exchanger power, and finally the system deactivation with the reduction of the water level, a reduction of the heat exchanger power, and the heat up of the fluid in the pools due to the missing to the end of the natural circulation within the two pools. So for this reason, we applied the accuracy evaluation procedure that we saw before, because we were interested to see if the code was able to predict the involved phenomena, the phenomena that we identified to occur during the test, and also to see if the quantitative value were correctly predicted. In this case, we saw that basically our code was the code was able to predict almost all the involved phenomena. In this case, with the exception of the tube side condensation, and we discussed it why this phenomenon was not correctly predicted, at least from a quantitative point of view at the beginning. And also the other phenomena that was not predicted was the thermal stratification in the pools, because another limitation of these computational tools normally is the simulation of large water pools. And so this can be an issue because in several passive systems, large pool of waters are adopted as heat sinks for decay heat removal system. And after this qualitative accuracy evaluation, we did also quantitative accuracy evaluation. In particular, in this case, we adopted, for example, this fast Fourier transform based method that is one of the possible methods to evaluate the quantitative core accuracy that gives us some quantitative values that can help us to say if our calculations are good enough in the quantitative prediction of the thermal hydraulic parameter values. So after this initial validation of the code, it was possible to pass to the uncertainty quantification, because as we mentioned at the beginning, the result of a single calculation cannot just be considered alone as the real value of our plant, because we know that we have some uncertainties. And in particular, we selected some uncertain input parameter based on previous references and engineering judgment. And for us, the main target of the analysis was to see how this uncertain input parameter may affect the calculation of the heat exchanger power, because it was one of the main parameter that we were interested to study. So we adopted the probabilistic propagation of input uncertainty, and we did it coupling the Raven tool that is developed by Idaho National Laboratory with the RELAP 3.5 code. Also, this code is developed by Idaho National Laboratory, and we applied the so-called Wilks formula to determine which is the minimum number of code simulations that we need to run in order to comply with the prescribed confidence level and probability confidence that normally is 95% for both of them. And we saw that in this case, we were interested to the minimum value of this simulation, because we wanted to see, considering all the uncertainty, which is the minimum power that our system can extract. And we see that considering, for example, the blue line on the right-hand side, we passed from 20 megawatt, that was the value of the reference calculation, to almost 16, to around 16 megawatt in the central part where we have an almost steady state operation. So you can see also from this simple example that we can have a large uncertainty on our results. And so for this reason, it's very important to carry out both the accuracy evaluation on the reference calculation, but also the quantification of the uncertainty. And then to understand how the input parameters and our figure of merits, so in this case, the heat exchanger power that we selected as the most important parameters are related. We use different approaches. In particular, we computed both correlation and regression coefficients to characterize this relationship. And this is very important also to characterize this relationship, because it helps us to understand which are the parameters that mostly affect our calculation. And so which are the parameters that we are interested to know better, in particular, because if we can reduce the uncertainty on these parameters, it is probably that we can reduce also the uncertainty on our results. And this is what we want, because we would like to have to know as much as possible better our results, because these are the results that, for example, we have to compare with the regulatory acceptance limit. So with this analysis, we are able somehow to correlate, to characterize the relationship between the input parameter and our results, and to see which are the parameters affecting the most our results. Then we did a second application. So the first one, as I already mentioned, was related to the decay heat removal system, basically for fission application. And we did also a second application to see if this methodology is applicable also in a passive system devoted for fusion application. So in particular, we considered the ingress of coolant event, that is a possible accident in fusion reactors. And in Japan, at JERI, there is a facility that was designed to study, to characterize from a thermal hydraulic point of view, the behavior of this event. In this case, the passive system is a pressure suppression system that has the goal of reduce the pressurization on the plasma chamber that can be caused by this ingress of coolant event. In this case, we adopted the trace code that is developed by US NRC to simulate the behavior of this kind of accident. And we developed the nodalization in the graphical user interface that is SNAP, that is a graphical user interface that is used to adopt the US NRC codes. And in particular, we adopt the same procedure that we consider for the PERSEO facility. So firstly, we did the reference calculation, and we tried to assess if our code was able to predict the involved phenomena and to correctly predict also the thermal hydraulic parameter from a quantitative point of view. And after that, we did an uncertainty analysis, in this case, with uncertainty tool Dakota, that is developed by Sandia National Laboratory. So this is the schematic drawing of the ICE facility. So we have two horizontal cylinders, one that simulates the plasma chamber and the other one that simulates the vacuum vessel. And there is the injection of water in the plasma chamber simulating the rupture of the cooling tubes. And the pressure suppression system is installed on the bottom side of the vacuum vessel. In particular, the pressure suppression system is this suppression tank where we have the discharge of the water from the vacuum vessel. This is a representation of the nodalization that we developed through SNAP for the trace code. And this is a quite complex nodalization because in this facility, we have multidimensional flow. So we have the injection of water horizontally, and then the flowing of water from the plasma chamber to the vacuum vessel vertically. So we adopted a three-dimensional nodalization. And we did also some analysis on the suppression tank, because since this was the main focus of our analysis, because this is the passive system that we are interested to study, we tried to understand which was the best modeling approach to model this component. And in this case, we saw that a more coarse nodalization with the single volume for the suppression tank provided better results compared to more complex nodalization. That is something that may be not always true, but in particular with thermal hydraulic system code, is not always it's not always true that with a more complex and finer nodalization we get better results. So as we said at the beginning, also the nodalization can introduce some sources of uncertainty in our calculation. So with our reference nodalization, we performed the reference calculation to validate our code, not our code, but to validate trace code for this specific transient. And we selected some relevant parameters such as the plasma chamber and vacuum vessel pressure, the suppression tank pressure, so on, comparing the code results with the experimental data. And as we did before, we identified the main phenomena, the main thermal hydraulic phenomena occurring in our transient, and we evaluated the code capability to correctly predict that. And we ended up, the results showed that trace code was able to predict all the involved phenomena from a qualitative point of view. And applying, again, in this case, the fast Fourier transfer-based method, we also evaluated that also from a quantitative point of view, the code was able to predict the behavior of the main thermal hydraulic phenomena. So after this accuracy evaluation, we validated the code for this specific transient. And we also wanted to, also in this case, to characterize and to evaluate the uncertainty of the result. And in this case, we used the Dakota uncertainty tool, coupling it with trace in the SNAP environment. And we selected also in this case some uncertain input parameters based on previous studies or engineering judgment. And also in this case, we selected which is for us the most interesting parameter in this case, that was the plasma chamber pressure. And based on, again, on Wilks' formula, we ended up with the minimum number of code runs to obtain the prescribed probability content and confidence level that normally is 95%. And so these are the results. And so in this case, I showed you also the spreading of the calculation, not only the minimum value that is compared with the regulatory limit. And so in this case, you can see that considering the different calculation, we don't have anymore a reference calculation, but we have a kind of a band, a cloud of results. And we have to see if our experimental data are somehow comprised among these calculated results, because in case it is not comprised among the experimental result, among the calculated result, we need to understand why there is some differences between the experimental data and the code results. So in this case, you can see that the experimental data is almost comprised everywhere in the calculated results. And so this is a good news, because we know that all our simulations, the combination of all our simulations are able to bound the experimental data. And also in this case, we calculated some coefficients. In this case, it was just correlation coefficient with the Pearson and Spearman correlation coefficient to characterize the relationship between the input uncertain parameter and the figure of merit, because they allow us to see which parameter mostly affect our results, and so maybe in the future to reduce the uncertainty on that uncertain input parameters. So in conclusion, some takeaway messages that I try to provide with these two exemplificative applications. So passive systems are being adopted, or they are envisaged in several advanced reactor design, both considering fission and fusion plants. And the tools that we have to carry out deterministic safety analysis to analyze the behavior of this system and of the plants equipped with the passive system, so best estimate thermohydraulic codes, should be validated against the phenomena typical of passive system, because these codes were mainly developed having in mind the phenomenology of active systems that were adopted in nuclear plants. I presented you a way to do this validation based on the evaluation of the accuracy of the code results. And in addition, it's not possible just to make a single calculation to validate that single calculation and to trust the result of that single calculation as the real value that has our system. But we need also to quantify the uncertainty on the results, because in a case of an experimental facility, we have the experimental data, so we are able to evaluate the accuracy of our code. So even with a single reference calculation, it may be enough. But when we go to full plant application, we don't have any more experimental data, so we cannot fully trust our reference calculation, even if the code is validated. So we need to quantify the uncertainty of the results in the view to move from a conservative approach to a BEPU approach. In particular, I presented you two applications with the two different passive systems, one that is a decay heat removal system and the other one that is a pressure suppression system, and with the two different codes and two different uncertainty tools. And in particular, in both cases, the selected code were able to predict the involved phenomena, even if some limitations have been observed, for example, in the evaluation of the condensation and transfer coefficient against the PERSEO facility data. In both cases, the probabilistic propagation of input uncertainty method has been applied to quantify the uncertainty of the result. And this method has been selected among the available ones because this method is suitable to be adopted in a computer code simulation, because it is based on the creation of a certain number of code runs with a different combination of the input uncertain parameters. And so this method is quite powerful for the calculation of the uncertainty of the results of the code. And finally, it is also important to apply some techniques. In this case, correlation and regression coefficients have been considered with the goal of characterizing the relationship between the uncertain input parameters and the figure of merit. So let's say the main parameters selected as output of the analysis in order, for example, to reduce the uncertainty of the parameters that mostly affect our results. Here you have some references on this specific topic, and in these references there are all other references for the methodologies and so on that if you are interested in. And with that, I conclude my presentation, and thank you very much for your patience. And if you have any question, feel free to ask.
Okay, yes, thank you, Dr. Bersano, for this very impressive speak. So do we have any questions from the audience?
Yes, I have a couple of questions. First off, thank you for the presentation. It's very interesting information. So you touched on the fact that there are certain parameters that you expect to have an effect on the calculation. How do you go about identifying these parameters, especially when you have a model that has a very large number of parameters? How do you kind of determine which ones of those may be important? And then in addition to that, the level of uncertainty that you want to associate with each of those parameters?
Yeah, thank you for this very interesting question. So it's a very hard task. Probably it's the most challenging task among all these methodology, because let's say the other steps are quite automatic, while in this particular step, the experience of the user plays a very relevant role. So one possible answer is by experience judgment. So it is expected that a safety analyst that makes this kind of calculation has several years of experience in the simulation of experimental facilities and full plant applications. So he should have an idea of which are the parameters that can mostly affect the results. The other piece of the answer is, for example, to make some sensitivity analysis at the beginning in order to understand if a parameter has a relevant effect on the output or not. And so combining the expert judgment of the safety analyst previous research on the field and eventually some sensitivity analysis, it is possible to reduce the number of parameters that mainly affect the results. Also because this method is applicable if it is possible to reduce the number of relevant parameter, let's say up to some tens of them, because otherwise finally the results are difficult to be analyzed, and maybe the uncertainty band is so large that it may be also meaningless. So this step of identification of the most relevant input uncertain parameter, and not only the identification of the parameter, but also how to assign them some reasonable range of variation and probability density function is a very challenging task. And so, for example, for this second part, so the to assign reasonable range of variation and probability density function, also novel approaches are being tested, such as, for example, so-called inverse uncertainty quantification that does almost an inverse approach. So starting from the experimental data, it is possible with very interesting methods to reconstruct, for example, the probability density function and range of variation of the input uncertain parameter, considering the code calculation. I hope that I answer your question.
Yes, thank you. That was very helpful. And then one more question with that. When you do the actual uncertainty analysis, are you changing one parameter at a time, or are you changing like all of them and seeing how that affects itself, or a little bit of both?
Yeah, so the power of this method is that the number of code calculation that are required to satisfy the probability content and confidence level prescribed does not depend on the number of uncertain input parameter, but depends only on the number of the output parameter. So in this way, it is very useful because it allows us to vary all the input uncertain parameters at the same time. And so in these particular applications, a certain number of code runs are set up by sampling different values of the selected uncertain input parameters and creating different models that are then solved with the code. So in this way, we can vary the input uncertain parameters all at the same time. Otherwise, if we vary a single uncertain parameter at a time, it's more likely a sensitivity analysis.
Okay, thank you.
You're welcome.
So, okay, so if we don't have other questions from the audience, I have one quick question for you. So I noticed you have experience on both trace and relab. Did you did any benchmark comparison between these two codes, code-to-code comparison?
Not on the same experimental facilities. So for different reasons, we selected one code or another for a particular application. But for example, for the regarding the PERSEO facility, there has been an activity in the framework of the NEA, OECD NEA W Gamma, with an international benchmark in which both RELAP 5, RELAP 5 3D and trace code have been adopted, and the reports, the activity is over and the report is in preparation. So in the future, it should be published. And so it can be an interesting example of a code-to-code benchmark against passive system experimental data.
Okay. And another question is, how you define the uncertainty source term? So how you decide which parameters could be important you want to evaluate? So sorry, can you repeat? How you decide your uncertainty source term?
Yeah, okay, so the identification, as I mentioned before, the identification is very challenging. it is mainly based on engineering judgment. So after a certain number of analyses on different experimental facility, on different plant application, the user, the analyst, has at least an idea on which are the parameters, the most relevant parameters. Then, of course, previous study, previous references on the subject are very useful to understand it. And finally, if the number of parameters is still very large, doing a sensitivity analysis can be useful to reduce the number of the parameters.
Okay. Okay, sounds great. Thank you.
You're welcome.
Okay, so if we don't have other questions, let's thank Dr. Bersano again, and highly appreciate your very amazing presentation today. Thank you.
Thank you very much again for your kind invitation.
Yeah, talk to you later Friday.
Yeah. So thank you again, and have a nice summer in Wisconsin.
Yeah, it's very good here, very beautiful.